My name's Tom Augspurger, talking today about GPU-accelerated cloud-native geospatial. Bit of a mouthful. Cool, so a few themes to keep in mind in the back of your head as we go through today. First of all, GPUs are very fast, astoundingly fast. They're famous in the news today for deep learning. A lot of the people in this room are probably familiar with the simulation, modeling, that sort of thing. The team I work on, the Rapids team, is working on GPU-accelerated data science libraries. So GPU-accelerated pandas or polars for tabular analysis, plugins for NetworkX for graph stuff, scikit-learn and scikit-image, all these GPU-accelerated variants of these CPU libraries. And all that software built on top of CUDA for NVIDIA GPUs, plus the cloud makes getting started with GPUs easier than ever. You can maybe say easy. There's still some challenges for sure, though. Especially if you're trying to really optimize it, get it to, NVIDIA likes to talk about the speed of light, get it going as fast as possible. That does take some care, but we'll see you can get pretty far pretty quickly. The bulk of the talk is going to be spent on just kind of like my ideal audience member is someone who's new to GPUs. They have some workload that they're interested in, maybe not sure whether or not it's a good thing for GPU optimization or not. So get some heuristics, get a little intuition for what sorts of things might be amenable to GPU optimization and first things to think about as you start down that path. And then, I just want this to be like collaborative, so figure out together, what are the right things in this geospatial world. So I have a bit of background in geospatial. My day-to-day isn't necessarily geospatial, but we can figure something out and make it work, I think. Cool. A few definitions. So my favorite definition of the cloud comes from Dan Morris. End of the day, it is just compute, storage, and networking. So a bunch of machines dedicated to those things. Millions of services built on top of those, but end of the day, just compute, storage, and networking. And crucially, programmable compute, storage, and networking. So I have an example here using the coiled CLI, but you could do the same thing with Azure or AWS CLIs or SDKs or point and click through the web portals, but gonna be submitting a job here to spin up a VM, do some work, and then shut down. And then change a parameter, and now you have 100 VMs doing the work. Change a parameter, and now you have 100 VMs, each with a GPU doing some work, if you have enough quota reserved for that. But point being, it's easy to get things going at scale. It's that flexibility is like a really nice feature of the cloud. And then you clean it up and your scale back down to zero. One thing that's really worth emphasizing, a lot of people have made the point, but compute and storage are generally separate in these architectures. So it's like the disaggregation of compute and storage, it's like the fancy term for it, but it changes a lot of things. From like the low level of what file format do you use, maybe you want like IceChunk or ZAR instead of NetCDF, to big like architecture things like how do you structure your data pipelines, your applications. This whole separation of compute and storage affects a lot of things. For the most part, I'll be assuming that your data's in blob storage, and then you don't really worry about scaling storage. It's just like magically there. You get nice throughput and all that stuff, but not a thing you have to really worry about as you're maybe scaling up and down your compute to do some big job or something. We'll be assuming blob storage for the most part. And then GPUs specifically fall under that compute side of things, along with things like TPUs, like Alex mentioned, FPGAs even. GPUs are providing that accelerated compute. We'll see some of that actually next, but we'll spend a lot of time not talking about compute, but we'll get there. For this example, I took this from the Pangeo discourse. It's like Tom Nicholas shared it. It's like a physical oceanography quadratic mean. I'm not quite sure exactly what it is, but we have a couple of arrays here, four-dimensional arrays, U and V. And by default, these are going to be using NumPy, and we'll put them inside this X-ray data set. And then also, to do some benchmarking, we're going to use this library called CuPyXArray. I can make this a bit bigger. Make it a bit bigger. Using CuPyXArray. So CuPy is a library for, it's like a drop-in replacement for NumPy that GPU accelerates NumPy on the GPU. And then built on top of Xarray as well. So CuPyXArray adds this CuPy accessor, and then we can get the data over on the GPU. Okay. So we have these two arrays here, U and V, and then the problem trying to optimize is to take the product of each of those variables, so U times U, V times V, and U times V. go ahead and run that. Oh, and then we take the mean of each of those products. And it takes 2 or 3 seconds or so on the CPU using NumPy. We can run the same thing on the GPU, and it's like 40 milliseconds. So I don't know, like that's 2750 divided by 33, 34, round it up. It's like a nice 100x speed up with like 1 line of code change. I'm cheating a bit, and we'll talk more about how I'm cheating, but yeah, it's like a really nice speed up there. If you're allergic to C++, I'm sorry, so CUDA kernels are traditionally written in C++. There's like a lot of nice things to make it accessible from Python, but I did it just for fun, wanted to. I'm learning CUDA. This was written with the help of AI coding tools and all that jazz, but really exploiting a lot of the structure of the problem to minimize the number of reads from RAM and doing some fun stuff with shared memory. Anyway, you can kind of see what's going on here, sort of. I don't know, but this is like load up that kernel, run it. It's like very, very fast. So like another 5x faster. So we've gone. I forget what the original. It's like a 500x speed up or whatever. And you can do the same thing in Numba. It looks a lot like C++, but it is technically Python. So same thing, and it's roughly the same performance there. So yeah, so that's just like hammering home that point. GPUs are fast. Also making the point that for NVIDIA GPUs anyway, you do have a lot of choices for how do I actually get started? So probably the easiest way to get started is like these literally zero code change accelerators where you like have this import plugin thing, Python-m, cudf.pandas, and then you have your pandas code. You don't change it at all, and if it runs on the GPU, it'll be accelerated using cudf. If not, it'll use pandas. Similar things for NetworkX, scikit-learn. So literal zero code change. You have like your minimal changes, like that last example, CuPy Xarray. Add an import, add that as CuPy, and then do your operations normally using these drop-in replacement APIs, all the way down to writing your own CUDA kernels if you really want to. Python is like getting much better support for writing those kernels, and then even if you are writing those kernels, you still have like. You're not going to write your own FFT or your own, linear algebra routine. So there's CUDA versions of all of those that are available to you, even if you are writing the kernel yourself. So great. So let's think through some workloads, cloud-native workloads. If at a high enough level, all workloads I think can kind of follow this pattern: is loading some inputs, computing something interesting, and then storing or somehow serving that output. So maybe you're making a cloud-free mosaic. In this case, you're loading this time series of imagery, stay stored as cogs on blob storage. You're going to do your computation, which in this case is like maybe reprojection, aligning pixels, and then doing that median, that reduction over time, getting out like a single layer, one per band or whatever, and storing that out or serving it to whoever's asking for it. This is from the Neural GCM paper, which I think Alex supported this work maybe, getting those nice data sets. Probably on Google Cloud Storage, you're loading these forcings and the inputs, and then training your model. So this was using JAX, using TPUs probably, but they have a CUDA backend as well to do all the back propagation, fancy deep learning stuff that I don't understand, but updating some model weights and then storing those model weights out. Maybe you're making some forecasts, so this is from the ForecastNet paper from NVIDIA, where you're loading in your initial conditions and the model weights from blob storage again, doing the prediction out for the next n time steps given those initial conditions, and then serving or storing those forecasts. So anyway, load inputs, compute, store results. And if we think about like where's the time spent, what resources are busy as we go through each of those stages. When you're loading inputs, it's mostly network bound. There's some compute as you decompress things. You can decompress like the Parquet columns or ZAR chunks. That's going to be using compute. I just mentioned like again, NVIDIA has GPU accelerated Parquet readers and ZAR as well. So you can speed up that loading of data, but you're going to be spending a lot of the time waiting around for the network. When you're doing the computation, hopefully mostly using compute, although there's caveats there around memory bandwidth. That's where I cheated earlier, but we'll see that. And then you're going to be storing the results. So again, mostly network bound, a little bit of compute to do the compression. If we turn that on the sideline and look at it as a function of time, you can see a few different kind of profiles, types of workloads. So in this case, we have an I/O bound workload where we're spending a lot of time waiting around, loading data. and a little bit of time doing our computation, but it's not too expensive. Store the data. Again, we're waiting around for the network mostly. And then we can compare that with a compute-bound workload where load the data relatively quickly, doing your computation, taking most of the time, and then you store the data. Okay, so as you're thinking about, okay, where do I get started? The I/O-bound workload is probably not the right place. So, to even get here, first of all, you need to be profiling. You need to understand where your time is spent. You need to be like, is your data loading slow because you're using the wrong file format, or is it really you're just waiting on the network? So anyway, in this case, we can GPU accelerate the compute, and it's a little bit faster here. This green bar is a little smaller, so our overall time here, this black bar at the bottom is again a little bit smaller, but it's not maybe not worth it. Compare that with a compute-bound workload where since compute was such a large proportion of the time originally, we can speed that up a lot, and now our overall time has really improved here. Okay. And then I do want to emphasize, like GPUs, they are accelerators, right? They're devices. They're part of a larger system. This is like, I don't know. It really is. This is like NVIDIA's new server class, Blackwell. I can't remember the exact name, but it's really cool. There's like a lot of GPUs in here. A lot of it, you can't see it, but a lot of networking. It's really cool. I assume most people are using like a single node or maybe a few nodes with multiple GPUs in it, but either way, whether you're using a single node or this fancy thing, it is part of a larger system that has a network interface card in it. As CPUs, it has RAM, both on the host side and the device side, GPU interconnects, and if you're paying for all these things when you're running these from the cloud. You're paying for all these things, so you might as well use them all efficiently to maximize your throughput or whatever your goal is. So one key strategy there is pipelining. So this applies as well to if you have like a multi-core CPU as well, but it applies even more so when you have a GPU, is the ability to like take a big problem, break it down into smaller units of work, and then do those work in parallel. So in this case, we have read in blue, gonna do the reading on the CPU, hand that off to the GPU to do the computation. It's nice and fast, it's GPU accelerated, we're great. And then we hand that result back to the CPU to store it somewhere. And then the CPU picks up the next task and then hands that out to the GPU, and keep on going through the full problem. This is not great because if you look here, the GPU is idle while the CPU is busy reading and writing. And actually, the CPU is probably idle here too. We're probably just like waiting around for bytes from the network. So it's really the network that's busy here. CPU is idle, GPU is idle, not really getting good utilization of any resources here. So with multi-core CPUs, but even more so with GPUs, we do have the ability, some cases, to do pipelining. We're able to start reading the first chunk or whatever of data, hand that off to the GPU, and then that first I/O thread is going to immediately turn around and start loading the next chunk of data. While the GPU is busy computing its result, when the GPU is done, it passes it along to some separate I/O thread or process or whatever to do, storing the data. And then we get full utilization of the network, of the CPU, GPU, everything's working together to maximize throughput of the entire system. I've drawn this as like a nice chart. You'll notice like all these things are like the same size, so the pipelining is nice and easy. We're not like sharing, communicating across chunks. So this is a challenge for many workloads. But maybe we can find the workloads where this does work out well enough that we can get like good throughput, maximize all the usage of all the pieces of our entire system. So I mentioned earlier bits about memory bandwidth. Like even if you are compute bound, like you've optimized your I/O, you have all these data loaders responsible for feeding data to the GPU. It is worth noting, like one of the first things you'll run into as you do GPU computing is that it has like most GPU systems have a separate memory hierarchy. So you have your main memory. This figure comes from the Flash attention paper. Quick aside, so attention was it was really important for LLMs, I guess. I'm not an expert. And then I don't know how many years later it was, but this group wrote up this paper on Flash attention. It was like a new algorithm, new way to do that. To do that algorithm, and it's like an I/O aware algorithm for attention, and it's like really focusing in on how do we think about how data flows through this algorithm that we're doing, tailored specifically to the chips, the types of chips that we're running this on. So it was interesting to think about like I/O, which is like probably the first thing you run into as you try and do this. Anyway, we have our main memory. That's great. It's, in this particular node they were working on, it has like over 1 terabyte, so you have a lot of space to work with, but relatively slow, so only 12.8 gigabytes per second on this chip they were working with to get the data from main memory to the GPU. So relatively slow, but once you get it there, the idea is you want to get the data to the GPU and then leave it there. You have less room to work with on the GPU. Again, typically it varies by card, but in this case, they had 40 gigabytes of room to work with there of RAM on the GPU to work with. Much higher bandwidth to get it from HBM, the high bandwidth memory, I think it is, to 1.5 terabytes per second, so much faster. And then even faster, so this is one of the tricks that I used in the quadratic means example, is this SRAM, which is like an L1 cache kind of. It's like 19 terabytes per second bandwidth there, but only 20 megabytes of that to work with. So anyway, the point being is like you might need to, if you're really going all out, you might need to think about memory bandwidth, but maybe just using CUPI is good enough and you don't really have to worry about this too much. So. And then, minimize the amount of transfers that you use, and then try and maximize the compute operations for each time you have to go out to memory to read or write some data there. So some things you might want to think about. Cool. So first thing, you do have to start with profiling your workloads. Hopefully you kind of have a rough idea in your head of like, okay, where's my time spent? Am I reading data from the network? Which I think like everyone I've talked to, like that's the pain, is like object storage is great. It's like super fast, but it's maybe a bottleneck unless you're really carefully using it, or if you're using Kyle's Augspurger library, it'll speed it up magically for you. Probably focus on compute-bound problems first. So like I mentioned, we do have I/O libraries like Quick I/O, kind of helps with getting data from either from disk or remote storage directly to the GPU. Or focus on like pipelining to avoid that I/O bottleneck. So you have some things there to help that out. I would say start at the high level. So things like Rapids libraries, CUPI, Torch and JAX, they all kind of have this array API that then compiles down to different runtimes. Earth 2 has like a bunch of, from NVIDIA, has a bunch of like things that you can just like, educational materials, but also like models that you can just pick up and use. Storage formats like ZAR have native support for GPUs, so start at the high level and then work your way down as you profile things and realize that maybe there's some additional rooms for speed up here. So cool. And then please do reach out if you have any use cases that you want to work on together. Reach out. Email is here. And thank you all for listening.